Thank you very much for joining us for this webinar. Affinisep develops and markets products in three different fields: food safety, molecular biology, and environmental applications. To promote the work our customers are doing with our products, we plan to hold regular webinars on these application areas. We are proud that Dr. Branislav Brana and Dr. Pavel Schauer have agreed to share and comment on the result of the Joint Danube Survey 4. This survey is carried out every 6 years to monitor certain aspects of water quality, such as biology, microbiology, hydromorphology, and chemical contaminations of the Danube rivers. We have named this webinar Innovative Use of Passive Samplers for the Characterization of Organic Micropollutant Mixture in the Danube. Today, Dr. Branislav Vrana, Associate Professor at Recetox, who has more than 20 years of experience in the field of passive sampling, will present the use of these passive samplers and silicone rubber to assess the chemical contamination of the Danube. Next week, on Thursday 6, from the same passive samplers, Pavel Schauer, specialized in vitro toxicology, will comment bioassay results. Do not hesitate to register for this session too. During the webinar, feel free to ask for any question in the chat room. First, my colleague Luna will present you Affinisep products related to passive sampling, and then we will follow with the presentation of Dr. Branislav. Thanks a lot.
Hi, I'm Luna. Nice to meet you. I'm working as a sales engineer for Affinisep. And well, as my colleague said, I will briefly introduce you Affinisep for those who are not familiar with us, and then will be the time for Branislav. So first thing first, who are we? So Affinisep is a French company created a decade ago, and it's an application-oriented company specialized in sample preparation. We have some US entity, and thanks to all of our distributors, we are able to sell our products worldwide. Our expertise, well, we develop and manufacture all of our polymeric resins from the beginning to the end on our unique technological platform to obtain specific resins with physical and chemical properties adapted to our customers' needs. So, well, thanks to our expertise and we can have some flexibility to provide you with some innovative products according to what you need, and so we can really create products for and with you. So Affinisep is working on three areas. First is food safety. Our products are really based on molecular imprinted polymers, say MIP, for the selective extraction of pesticides, mycotoxins, antibiotics, pH on food and feed matrices. Our second area is environmental analysis with passive samplers, and that's the main topic today. And we also have a third area, which is bioanalysis and proteomics, which is for sample preparation in proteomics, such as peptide desalting, fractionation, purification, etc. But now let's speak about environmental analysis. So to better understand this field, we need to ask ourselves a few questions. So the first one is, why use a passive sampler? So there are a lot of benefits. First, a passive sampler doesn't need any power, maintenance, or supervision. You just put your passive sampler in the river for some time, so it's really easy. You can detect spot release, and have some average concentration to limit variation, which is not the case with more common grab sampling, for example. It doesn't need specific condition for storage, so here also it's quite easy. You can have a lower limit of quantification due to the concentration of the contaminant of the passive sampler, and it retains chemical information. That means there is not metabolism or another reaction. One of the biggest advantages is that they enable easy combination between chemical and biological analysis, and it's interesting because will see this in our presentation of this week and the second part next week. Finally, we have passive sampler for all different fields, so for seawater, surface, and also groundwater. As you saw, as you can think, there are a lot of passive sampler according to what you want to analyze. So which passive sampler for which application? So first, for polar contaminants, there is two different types. The first one on the left, it's named POSI. So it's for polar organic chemical integrative sampler. And the second one is a passive sampler based on disk. Maybe on some publication you saw the name ChemCatcher. It's the same technology, but it's the name of a brand. So there are for polar contaminant to catch pesticides and drug residues. We also provide POSIs specialized to catch glyphosate and its first metabolite AMPA. And we also have POSIs for PFAS. So we can provide POSIs with or without PRC, which is an internal reference, which enable us to correct the value you will have in the field. So for the other type, which is the one used on the webinar, you will see later. So for disk, you can have different sorbents like HLB, C18, RPS. So it can enable you to focus on which family you want to capture. And one of the advantage or particularity of passive sampler based on disk is that you can use it with or without diffusion membrane. I will explain it in the next slide. So for non-polar contaminants, you have silicone rubbers, which you can put on, let's say, some spider holder. It's to catch some hydrophobic micropollutants like PCB, pH, etc. And this passive sampler was used for the Danube survey that you will see on the webinar. Our last passive sampler is named SPAT. So it's for solid phase adsorption toxin tracking, and it's for microalgae toxin in fresh and seawater to catch different biotoxin families, such as ASP for amnesic shellfish poisoning, DSP for diuretic shellfish poisoning, or also paralytic shellfish poisoning. So these four different passive samplers need to be on some orders. You can see on the top right of my slide. So, and this order, you can put it on some canister. You can see it on the other corner of the slide. It could be like little, middle, or big canister if you want to have 1, 2, or 3 order with 3 different POSIs or disks, or if you want 1 or more silicone rubber. So these canisters are used to protect your passive sampler from some big contaminations, such as the wood, trees, or something which could destroy your passive sampler. And finally, we have some alternative format for groundwater for any passive sampler. As you could imagine, in groundwater, there are a lower level of water, so you really have to adapt the format, and that's the thing we have. So just to explain a bit, as I told you, we have 2 different passive samplers for the same contaminants, the same group of contaminants, which are polar microcontaminants. And I just want to explain you the major difference. So the 2 are based on some housing in metal, and in between you have a disk or a sorbent, which is a powder, which is for POSIs. And for POSIs, you have 2 diffusion membrane, and for the disk, you have only 1 diffusion membrane. So the disk can be used with or without this filtration membrane. It's an easier extraction of contaminant from solid phase. We could provide you with some refill kits. So It's like only the SPE disk and the diffusion membrane, you keep the housing. And the window of exposure is of 40 millimeters. On the other side, we have POCs which are really specific for PFAS or glyphosate. We supply this with empty SPE columns frets to transfer the powder and to make yourself the extraction. And here the window of exposure is larger. It's 2 times 55 millimeters. So the big advantages of disk is that you can use without the filtration membrane. So that means you will have a faster accumulation, thus shorter time of exposure to work on the linear accumulation. And that means you could catch a broader range of contaminant. On the other side, the POCs have the biggest exchange surface as they have a biggest windows of exposure. So now let's go into the heart of the matter. How does that work? So here I take the example of disk passive sampler as it's the main passive sampler that Brana will speak about. So first you put your disk-based passive sampler on the holder. You put it on some canister to protect them, as I told you before, and you have to think about the right place to put them on the river for a few days to months. It depends on what you want to catch and the place where you are. After this time, you recover the disk. You will dismantle the housing to take the disk and to make some elution with methanol on the disk manifold. Then this methanol extract will be sent to laboratory to have some result. But well, in the environment, there are 3 different stages of the concentration of contaminant on your passive sampler. It's linear, curvilinear, and equilibrium. So most people want to work on the linear part. You will see that Brana work more in the equilibrium part, but he will explain you later. So, well, people want mostly to work in the linear part to have some quantitative result. Indeed, when you send the methanol extract to the laboratory, you will have a concentration of contaminant in your disk or in your powder if you're working with POCI, but you don't have directly the value of concentration contaminants in water. So for this, you have to use the equation in the lower part that I have written in the lower part of the right. So to have the mean concentration of contaminant in water, you miss one value, and it's what is named RS, so sampling rate. So to obtain this sampling rate and thus obtain some quantitative results, you need calibration. So you do some calibration in laboratory with a tank that you will fill with water. You put your passive sampler, it could be POCs or disk, and you add some water to make some flow, the same flow rate, which will be could quite similar of the flow rates that you will have on your river, on your lake. It depends on where you do the analysis. So in the tank, you will add some speak solutions that of a contaminant you really know the concentration, and then you will analyze the concentration of resulted contaminant. So thanks to that, you will have some sampling rate for specific molecules, and thus allowed you to put your passive sampler in the field and then have the real concentration. So we have done that for 13 different PFAS, from the lower carbon chain such as PFBA to a longer carbon chain PFDA. And you can see on the left two of our calibration curve with a good correlation rate. So, and we are currently working to add more PFAS to help our customer to provide more quantitative results for their PFAS analysis. So after all of this question, here is our solution. service possesses PFAS. So we provide you with 100 supports for the whole duration of your project, from training and technical support from the beginning to the end of your project. Obviously, we provide you with consumable and accessories, and then we recover your sample, your POCs, and do the analysis in laboratory and send you back a result and report. So for now, our service is only for POCs and in the aim to analyze PFAS. So we do that for monitoring of PFAS concentration before, after some strategic points. So, for example, some factory, wastewater. It's for qualitative and also quantitative monitoring for custom-made service. So if you have any question, just don't hesitate to ask us a question or contact us. So thank you for your attention. And now,
thanks a lot, Luna. Now we will listen to Branislav and to show the result of the Danube survey. It's up to you, Branislav.
Good afternoon, ladies and gentlemen. I would like to first thank to Luna and Michel from Affinisep to give me the opportunity to present some results of my research. My name is Branislav Vrana. I'm an environmental chemist working at the Masaryk University in Brno, Czech Republic. And I will share my presentation with you in a second. I hope this is now well visible. So I will be talking about micropollutants in the Danube River using an innovative approach, and that is long-term exposure of passive samplers. Before I start talking about the passive sampling application, I will explain the background first, and that is the study I'm going to show was conducted in the Danube River. The Danube River is the second largest river in Europe that flows 2,800 kilometers southeastward from Germany to the Black Sea and collects water from a river basin that includes 19 countries and more than any other river in the world. The catchment area is nearly 800,000 square kilometers, representing approximately 8% of the territory of Europe. And it on its way, it passes through numerous municipalities, including 4 capital cities, that is Vienna, Bratislava, my hometown, by the way, Budapest and Belgrade, and then runs through 9 countries. In the middle, you see this pyramid, which shows the average discharge that was in summer 2019 when this study was conducted during the monitoring activities of Joint Danube Survey. And we can see that at the site 1 on the left, that is the upper Danube, the discharge was about 1,400 cubic meters per second. And in the delta area, in the lower Danube, the Danube is much bigger. Its discharge is over 6,000 cubic meters per second when the Danube drains to the Black Sea. 83 million people live in the Danube River Basin, and over 20 million people depend directly on the Danube for their drinking water. And on the right-hand side, you can see that the upper Danube has a very higher population density within the 50-kilometer band of the river than the lower Danube, which is more rural, and there are some peaks on this diagram showing the big cities on the Danube River, like Budapest or Novi Sad or Belgrade and downstream Rus and Galati. So the water is used for different purposes as a source of drinking water, but it also receives treated and untreated wastewater and is affected by a wide spectrum of pollution sources from the catchment. So given that the Danube drains a substantial area in Europe, joint research efforts addressing its contamination with organics are essential for good water quality management, reaching beyond the borders of individual states. That's why this Joint Danube Survey is organized, which is every 6 years, and is one of the largest river expeditions, scientific multidisciplinary monitoring surveys in the world. Michel already spoke about it. So the survey really covers all aspects of water quality and quantity in the river, and its objective is to produce representative, reliable, and comparable information on selected water quality aspects. Since the Danube is used as a source of drinking water, but also receives wastewater, the characterization of the presence of pollutants, pollutant mixtures, and risk prioritization of pollutants is very important. So our study that I'm going to present this week, and then my colleague will follow the next week, is to provide information on organic trace pollutants, which could serve as a baseline for water quality monitoring in future Joint Danube surveys. Investigation of temporal and spatial pollution trends over several years requires the use of representative sampling methods, and that can characterize the contaminant patterns and their levels in the river water over a longer period of time. So the aim was to test such method using passive sampling, and the next week I'm going to address this from the chemical point of view, but my colleague will then follow with ecotoxicological assessment, where he tried to identify also substances that are responsible as a toxicity drivers in these complex mixtures. In our study, we proposed potentially applicable methods for sampling organic contaminants in water based on passive sampling. And the main task was to passively sample a broad range of compounds to determine their levels and to relieve the composition of the mixtures. The samplers were deployed in the current of the river at 9 representative sites, which are shown here on the map with the yellow dots. And the deployment was static and from May till beginning of September. So the samplers were deployed altogether over 100 days. And the main results of the study were published and are available in the scientific report published by the Danube Commission, and in a scientific paper that has been published in Environment International, you can see on the lower right hand side. So why we use the passive samplers for the monitoring? Passive samplers are basically tools that, in contrast to conventional grab or spot sampling method, due to its continuous sampling over several weeks, provide some more representative approach for the characterization of pollutant mixtures over a long period of time. And the passive sampling is actually a process where you insert sorbent or polymer to water, and it by partitioning or adsorption collects the chemicals from the water and until it equilibrates with the water. So it doesn't require any active source of energy. The interesting aspect is that you can accumulate in the sampler quite sufficient amount of chemicals, not only for chemical analysis, but also the extracts can be subjected to bioassays and with visible effects, which is then was used in this case, and my colleague Pavel Schawer will talk about it next week. The basic rule is that the passive sampler sorbent or the polymer have a constant and well-defined properties, and this is the main rule of environmental monitoring. So if we want to compare the data in time and space, we need to use a matrix which has well-defined properties. Concentrations in the sampler at equilibrium with water can be compared in time and space, which allows us to identify spatial contamination trends or temporal trends, and also to estimate with some uncertainty, though, the aqueous concentrations of the chemicals. The one passive sampler in principle does not allow the retention of all chemicals present in water because they have a broad range of properties. And this diagram shows the distribution of frequently monitored groups of compounds in the aquatic environment according to compound polarity on the x-axis and volatility on the y-axis. And this is actually the chemical space, and the domains effectively retained by different sampler types there are two such main domains. It's polar compounds, where we apply mainly absorption-based passive samplers, and then the hydrophobic compounds, non-polar compounds, where we use the so-called partitioning passive samplers, where the analytes actually diffuse into polymer and are dissolved in it, like in adsorption samplers in surface sorption. In the Danube survey, we to cover the as broad as possible part of the chemical space, we applied two passive samplers, adsorption samplers based on AttractSPE HLB Disks from Affinisep on the top left, which retain mainly polar compounds, and then silicone rubber sheets, which retain non-polar hydrophobic substances. And this way, the extracts then, after exposure in water, are subjected to targeted chemical analysis, where we were able to quantify a quite large number of compounds like industrial compounds, pharmaceuticals, pesticides, and for hydrophobic compounds, persistent organic pollutants, polycyclic aromatic hydrocarbons, pyrethroids, musks, aromatic amines, and other. Samplers were deployed in surface water using such stainless steel frame holders at a depth of approximately 1 meter below the surface. Samplers were hung by ropes from bridges, buoys, jetties to keep the sampler holders floating in the water column. And the samplers, which you can see on these pictures, accumulated organic compounds from the Danube water for approximately 100 days. Following exposure, we cleaned them on site from debris and fouling using local Danube water, inserted them to glass storage jars, and brought them cooled at 4 degrees to the laboratory as soon as possible, where they were stored at -18 degrees until processing. Now, Luna already explained you the theory of passive sampling. So when we deploy a sampler into water, it accumulates the compounds in time, and there are 3 stages of uptake. In the beginning, it's a linear, so it's the so-called integrative sampling, which is used a lot in the scientific community or also by end users. This is especially used when the deployment time is short, and the advantage is that what you get from the sampler is the reflection of time-weighted average of the concentration in the sampled water over the entire exposure period. But when we go to long exposure time, then the uptake reaches a plateau when the concentration in the sampler is at equilibrium with the sampled water. This curve has two important parameters that characterize it. It's the sampling rate, that is a compound-specific volume of water cleared of chemical by the unit of time, and is like proportional to mass transfer coefficient from water to the sampler. So it's a kinetic parameter, and then there is an equilibrium parameter, which is distribution coefficient of a compound between the sampler and the water, KSW. So after a long time, when assuming constant KSW value of individual compound at all sites, the ratios of accumulated amounts at different sampling sites equals the ratios of concentrations in water. So this implies that in an ideal situation, when we have equilibrium passive sampling, then results at the different sites are directly comparable and enable the identification of spatial contaminant trends. So enough of theory. Now I'm going to show you some results. First, I will start with the results obtained from analysis of the silicone rubber. These are already on these graphs, which I'm going to show in a row, are always estimated environmental concentrations from the uptake to passive sampler. So it's converted already to aqueous concentrations. Polychlorinated biphenyls are persistent organic pollutants regulated by the Stockholm Convention, and we can see that the freely dissolved concentration in the Danube river water is up to 300 picograms per liter as a sum of 7 indicator congeners of these polychlorinated biphenyls. The highest concentration is of the congener PCB28, which also has the highest water solubility. And the most burdened site, by surprise, was the last site, which is close to the delta of the river in Galati. Besides local sources, because the site is an industrial city, we assume that there are historically polluted PCB sediments in that area, and these compounds are slowly mobilizing to the water column, and this happens. Now these are brominated diphenyl ethers, which are also regulated by the Stockholm Convention. These compounds are much more hydrophobic than PCBs, and also this is reflected by the concentration in water, which is 1 magnitude lower than those of PCBs. Among the congeners, PDE congener 47 dominates in the dissolved phase at all sites, and this is in agreement with the knowledge that this congener is typically the dominant congener in technical mixtures when they are applied. So this is also reflected then in the water phase. But also it's better soluble than the very hydrophobic ones with the higher number of congener. The spatial trend here is different a bit than for PCBs. Elevated concentrations are found in the upper and middle Danube, and In contrast to PCBs, the lowest concentrations were found at the site 9 near the city of Galati. This graph shows the estimated cumulative aqueous concentrations of some organochlorine insecticides. Those are hydrophobic substances. Most of them are also regulated under Stockholm Convention and Water Framework Directive and should not be actively used. And we have the image that actually, despite the fact that there is a potential dilution of chemicals due to an increased discharge of the Danube with the distance from its spring, concentration in the Danube of these compounds increases with the maximum in the lower Danube, and it seems that these compounds appear in water again by mobilization from historically contaminated riverbed sediments, and with some they have a long half-life in the environment, so it will take another couple of maybe decades till they completely disappear, although they are not used. Now, this diagram shows the principal component analysis, which is like pattern analysis about where we can find what types of chemicals in the Danube from those hydrophobic substances. So we can see on the right-hand side that the compounds, which are these blue lines with the ends that sometimes cluster together, show that some compound classes occur together in the Danube, and where they occur is shown on the left-hand side. It indicates like on which sampling site approximately is elevated concentration of which group of compounds. So we can see that, for example, pesticides banned in the EU and some PCBs show elevated concentrations in the lower Danube, that is the red ellipse, whereas polycyclic aromatic hydrocarbons show the highest concentrations in the central middle part of the Danube, and the polybrominated diphenylators and some industrial chemicals, they are occurring more on the upper Danube. The second large class of chemicals are the polar contaminants, and in contrast to silicone rubber, the AttractSPE HLB disk sampler is designed to sample dominantly polar compounds, but it samples also hydrophobics, but I can later explain why we used this separation. The AttractSPE disks were chosen because this sorbent material has a very convenient properties for being used as a passive sampler. It's a N-vinyl pyrrolidone divinyl benzene based copolymer, which contains functional groups which are hydrophobic, and also some of them are hydrophilic, so they can retain quite broad range of compounds by different types of interactions, like hydrophobic retention or also other types of like polar interactions. It's stable in a broad range of pH, is water wettable, and can be used in passive samplers because it's flat, has large surface area. So, for example, in ChemCatcher, we put them in such steel disks, and in this case, unlike typical use, we didn't cover them with a diffusion membrane, but just with a protective nylon mesh, but it was only to protect it from mechanical damage. And we exposed it for 100 days. And we tested in advance the feasibility of equilibrium sampling, a hypothesis, with these disks. So we deployed these naked disks up to 100 days in effluent of a municipal wastewater treatment plant in Brno. And the example of these two drugs, carbamazepine and tramadol, shows that for many targeted compounds, an equilibrium between the sorbent and the water is established after this long period. We also were able to derive the distribution coefficient between sorbent and water, and that means that if we know these distribution coefficients with some precautions, we can semi-quantitatively estimate also aqueous concentrations, but assuming that the distribution coefficient will not dramatically change between the sites, we can identify clearly the spatial gradients if the concentration differences in water are high enough. And now the results from the survey. So I will show different classes of chemicals. This is for pharmaceuticals. I will start with antibiotics. 16 out of 29 analyzed antibiotics were detected in the Danube samples. And the highest concentration had the antibiotic trimethoprim, about 20 nanograms per liter at the site 4, which is downstream, well, on the border between Hungary and Croatia. Elevated concentration of clarithromycin was also detected at the site 1, which is the border between Germany and Austria. In general, the concentration decreases with downstream distance from the source. So, as I said in the beginning, with these pharmaceuticals, it's probably coming from municipal wastewater, and the density of population and the number of cities connected with the sewer systems to and the treatment plants to the Danube is it's proportional to the population density, which is higher in the upper Danube than in the lower Danube. Now, cardiovascular drugs nicely show that really higher concentrations are much higher concentrations are in the upper Danube than in the lower Danube, and hydrochlorothiazide was present as a dominant substance and only in the upper and middle Danube, and the second highest concentration was for metoprolol and then telmisartan. And we can see that the concentration decreases in the lower Danube quite dramatically. The same can be seen for psychoactive drugs, like here the highest concentration was for this N4-methylpyrimidine, which is a transformation product of a drug. And also relatively high concentrations were seen for metabolites of carbamazepine. Antihistamines, they were present but at quite low concentrations, but with clearly decreasing concentration trend downstream the river. And now the other group of chemicals I'm going to show are pesticides, and here we can see quite a different pattern of contamination. In the group of fungicides, the compound with the greatest concentration was boscalid, and then tebuconazole and demoxystrobin. But we can see that the elevated concentrations are in the lower part of the Danube, especially here you can see at site 6, which is downstream the Iron Gates Dam, and the site 8, which is Ruse in Bulgaria. And here for herbicides, we can see a similar pattern, nearly doubled concentrations despite the dilution factor and the larger discharge at site 6, 7, and 8, where terbutylazine, dimethenamide, and metolachlor were the dominant compounds. Lastly, insecticides. Here we can also clearly see the increase as we go downstream to the agricultural regions, because this is related probably that in this lower part, rural part of the Danube, there is a much more intensive agriculture than in the industrial upstream part of the river. Here we can see compounds like neonicotinoid, thiacloprid, or carbaryl insecticide. This graph only confirms what we saw, that we see dominantly higher concentrations of pharmaceuticals and illicit drugs and benzotriazole and some pesticides that have a mixed use in the upper Danube, and typically chemicals that are used in the agriculture, like pesticides, in the middle and lower Danube. And then I come to the end of my presentation, so I would like to conclude that this extended deployment of passive samplers provided more representative samples of seasonal contamination pattern and spatial distribution than what can be obtained by simple spot sampling of water. And these two samplers, the AttractSPE HLB Disks and silicone, provide a complementary picture covering broader range of chemical space. In the upper and middle stretches of the Danube, the occurrence of polar contaminants is associated with the discharge of municipal wastewater to the river. And in the stretches downstream the iron gates, application of pesticides in agriculture and mobilization of old pesticides from historically contaminated sediments present the main sources of micropollutants. I would like to thank, of course, Affinisep for giving me the opportunity to present, then my university and the Center ECETOX and its research infrastructure, the Danube Commission for creating the possibility to conduct this research, the Norman Association for which co-funded this activity, and the Czech Science Foundation, which helped us to exploit the results and write the scientific publications. And I thank you all for your attention.
Thanks a lot for sharing with us your experience and these results. That was very, very interesting. So I remind you that next week we will have Pavel explaining us about in vitro toxicology based on the extraction of passive samplers. Thanks a lot, everyone. Have a nice evening. Bye.
Bye.
Thank you. Bye-bye.